All right. Welcome, everyone. In the next 30 minutes, we are going to discuss how query performance and data management accelerations can be performed in Presto using Hudi. My name is Sudha Saktheeswaran. I'm a PMC member in the Apache Hudi project. I'm currently head of open source at Onehouse. Prior to joining Onehouse, I led the data lake efforts at Moveworks, which is a startup chatbot AI-based company. Before that, I was part of the Presto team at Uber, where I contributed to the early integrations of Hudi and Presto. And prior to that, I was part of different data infra teams, both at Uber's marketplace teams and LinkedIn's data infra teams. So for the agenda today, I'll walk through Apache Hudi, the data lakehouse platform, and dive into how Hudi's multi-modal indexing accelerates query performance, and how these optimizations can be leveraged in the Presto Hudi connector to support query accelerations. Okay, let's get started. Hudi was born, just to give like a motivation on like the origins of Hudi. Hudi was born in 2016 at Uber, where Uber was going through a hyper growth mode, where they were moving from a data warehouse to data lake kind of architecture. And the problems that Uber faced at that point in time were complex in terms of scale and the complexity as well. There was absolutely no control over concurrency or ACID transactions and things like that. Specifically, if you take a look at this use case here, they would have to ingest trip change logs like every 8 hours once, fully recomputed. And back then it was like 120 terabytes of data or so, recomputed every time into raw layer, which are Parquet files, and that exposes to ad hoc analysis. And further downstream pipelines would consume off of this raw layer to build derived data and pipelines, and those would also like recompute every 8 hours once. So typically the end-to-end latency is like 24 hours, the data freshness, and that wasn't acceptable at the rate Uber was growing then. So as you can imagine, there is like a lot of wastage of resources in this kind of an architecture. And if things go haywire, like when this is running in production, if something goes wrong, a job fails, you can imagine how you'll have to chase these jobs down the DAG to clean up, retry to make sure they are successful. And this is completely getting unacceptable, right? So to think about like how do we like redesign a solution for handling these use cases? So back in Uber, we were thinking about this problem and asking us questions of this sort, right? Like, can we actually consume only the changes which are less than 500 GB and not have to reprocess all the 120 terabytes of data every 8 hours? And would that help us also process the changes faster, like not just getting the change log just for the 500 GB change log, but also how to absorb that into the tables like quicker. And can we also stream these changes so that from the data lake table so that the downstream pipelines can build off incrementally instead of having to fully recompute? And while all these are happening, can the readers be isolated from all the partial writes or dirty writes or whatever is happening in the pipeline and just expose like clean slate data for the users? So these were the primary motivations for the core primitives in Hudi: upserts, incremental querying, and snapshot isolation. So this became like the architecture, the new architecture became like this, as shown in blue box here. The upserts now took just 10 minutes for consuming those 500 GB of data every time. And further, the downstream pipelines were also incrementally built, bringing down the total freshness latency to 1 hour from 24 hours. This kind of propelled more use cases, and Hudi started gaining momentum within Uber and across the industry. And this is what Hudi looks like today, and it's much more beyond table formats, if you will. It's a comprehensive data lakehouse platform and is mainly designed for ingesting and processing data from multiple sources. The features and services that Hudi comes along with are like more comprehensive and like seems more closer to the database like experiences. Offering things like table services and optimizing the tables, managing them and keeping them in like a process level so it can be easily plugged to or connected to different query engines of your choice. So taking a high-level overview here, the foundational block here is the data lake storage. And that's where all the actual data lives. And this could be any of the DFS kind of DFS-compatible storage, like cloud stores or HDFS or anything like that. And the file formats are usually the popular file formats like Parquet, Avro, etc. So what Hudi does is, after a successful ingestion and processing of the data from different sources, like databases or data streams or even cloud storages, it uses these, it builds like a transactional database layer on top of the storage that provides all these capabilities like asset guarantees, concurrency control, table services, etc., among others, and connect this processed, optimized data to different query engines like Spark, Presto, Athena, etc., for ad hoc analysis. And this is how the optimizations are also cascading in form of query acceleration to the engines that are plugging into the data. So just to give a quick glance, Hudi is proven at massive scale in different lakehouses. These are quick samples of open source companies that are using Hudi in their mission critical applications. Just to take a quick glance, ByteDance, TikTok is using Hudi, and one of their use cases, just like a single table that is at exabyte scale. Even at that level, Hudi brings the analytics from days to, hour kind of latency. So having talked about that, let's move on to the next section. I really want to talk about how Hudi's multi-modal indexing accelerates the query performance, and build on this for how this translates to the Presto support. So let's take a quick look, right? Like keeping aside Hudi, when you think about query performance, the key factor is like how do you reduce the number of bytes scanned from the table? That's the key thing to consider. There are three aspects to it, right? Indexing, caching, and storage layout. Indexing comes in handy for locating records quickly, and this is useful especially for queries that finds like needles in haystack and needs to return like very limited number of records back. So this is where indexing kind of comes into the picture. The second is caching, and this is applicable for queries that are repeatedly accessing the same type of files and blogs, and something like a read-through cache can help speed up the query performance for these kind of use cases. And the third aspect is storage layout, right? The storage layout basically leverages how the data is organized in the storage itself, and something like bucketing or clustering kind of optimizations benefit these queries, which where the records are where the predicates belong to records that are from the clustered files, and it helps narrow the number of files scanned as opposed to an unclustered table where you'll probably end up scanning the whole table, like leading to large number of data files that are being scanned. So in this talk, we will not be going through caching and storage layout. We'll just be focusing on the indexing part. So indexing is a widely known concept, right? Like nothing new in there. It's pretty much adopted by database systems like RDBMS and data warehouse systems. Mainly used for locating records quickly. You can consider like this similar to how you would use books index page to locate the data. And Hudi uses these indexes in different places to locate the records and also to process the upserts faster. So Hudi comes with different index type implementations already in top of the shelf. Some of them are the Bloom-based index, bucket index, simple index, HBase, and so on and so forth. Here is a quick high-level diagram comparing the implication of having an index in your platform and not having an index. If you take a quick look at it, you'll notice that in a system where there is no index, there is no notion of how your records are placed on your system. So what that means is every time when you have updates, you will have to process and merge these updates with every data file in the table. And this is going to be like too expensive as your table grows. Compare this to like a system which has index, which has a notion of how these records are placed. Now, the merging of these updates and deletes for the records are narrowed down to a specific set of files, or like even just one single file. Now, the merge cost is like drastically reduced, and this is like a very high level picture of comparison, but you get the idea of the impact of having an index and not having an index. This particular blog goes through a list of all indexes supported in Hudi and in which particular workloads or use cases different index would be helpful. If you want to check out, or feel free to read through the blog. The reason I brought the index is like I wanted to connect this with how we will leverage the query performances. Taking a seat back, if you look at how the query planning execution happens at a broad stroke, the first thing that happens is collecting the metadata. And the second one is query planning, applying some optimizations, and then actually reading the data before serving them. And as you can see, the first opportunity where you can improve the query performance is the metadata. And this is where I want to connect the indexing. Hudi offers multi-modal indexing. And what it means is it has structured the multi-modal indexing as a table inside Hudi. Any Hudi table would have a multi-modal index under its internal table, much like how Kafka has internal checkpoint topics, right? And this multi-modal indexing table, like the metadata table, is structured in a way that it has partitions, and each of those partitions are different types of indexes. For example, these indexes would be like files listing, or like a column stats index, Bloom filter index, record index, and functional index, and so on. And the way Hudi has designed the multi-modal index is it's super easy to create and drop indexes using SQL statements, and they don't block the ingestion. You can build these indexes in an async way. That's pretty much like how the multi-modal index is designed. Let's quickly take a look at the record level index. I wanted to connect this with the multi-modal index. We saw how for the query performance improvement, metadata is the first opportunity where you can leverage the index to gain the query performance. And in connection to that, I want to highlight how the record level index in Hudi, which is released in Hudi 0.14, is designed to be a part of the multimodal index, meaning it is a specific partition under the Hudi metadata table. Like just going back to the previous page, these are all different partitions, the files, column stats, these are all different partitions under the metadata table, and record level index is also a partition under the metadata table. What it has is a record to file location mapping, and this aids in faster lookup of records when both in the write and the read side. For the write, this is needed because you have the precise location of the record, so you can directly accelerate your upserts. And for reads, this is also useful for queries that have equality filters on the record keys. The challenge I just want to go through the a little bit context on the record level index. Hudi, I mentioned earlier that Hudi has different types of indexes already, and so the question is why did we have to build a record level index, right? The challenge before we developed the record level index was that the equivalent of this for a record to a precise data, like a file mapping, would probably be implemented using a HBase kind of an index in Hudi that is also available. But as you can imagine, if you want to build a HBase index, you also need to maintain a HBase cluster. And that kind of a maintenance is like an external dependency and requires dedicated resources or expertise to scale the cluster and also maintain that as a separate thing apart from your lakehouse tech stack, right? So this is kind of a barrier to entry. So we thought like, okay, let's make this all simple in terms of operation. Let's build an index that is in-house, sits along with the Hudi table. So the users do not have to maintain or go through like a separate HBase cluster on their own. But the benefit of HBase is like HBase has this H file format, which is easy for pointed lookups, like keep lookups instead of having to scan the file, right? So the record level index kind of borrows inspiration from this to be able to support like pointed lookups. And that is also part of the metadata table, the record level index. The reason is, imagine if you were to build this index information from the data files, and if there are so many data files in your table, you will end up anyway scanning those data files to get this index information, and that is counterintuitive to what you wanted to do. So the record level index is located under metadata table, which is a separate internal table and has very small number of files that just has the metadata information that you can quickly scan instead of having to scan all the existing data files to build this index information. So the way the metadata table is implemented is it is designed for fast index lookups because metadata keeps changing as you write data to your table. So it supports H file format for for storing the metadata. For the pointed lookups, and it internally uses a Hudi MOR table that is inherently designed for taking on upsets. So with that, let me get quickly into how like the record level index works on a high level. Like I mentioned, record level index is a partition under the metadata table. So if you have a new batch of records that are coming in, what would happen is these records are hashed to like a specific file in the file group in the record level index partition. And this hashing is literally no cost. And then from the file group, you have different file slices. Think of it as versions of data. And the latest file slice would mean the latest snapshot of the table, meaning here we are referring to the metadata table itself. So from the record key, you find the file group, get the latest information on where that record is in your table. To get that, like the leaf node is basically a data file, which is of H file format that has this key to value mapping, which says, this is your record key and this is your file location. So if you have this record key, here is where you should find the data file corresponding to this record key. And we don't have to scan the entire H file. Instead, we just do point lookups. That's the benefit that comes along with the H file format. So this is how the fast lookups are enabled at a very high level without going into the in-depth picture. So we did like performance benchmarks on this record level index. And what we did is we did the performance benchmarking on both the write and the read side using Spark. For the write side, we took like 1 terabyte data set and simulated it with like 200 megabytes of batches, where all those 200 megabytes represent the updates that are coming to that table. And what we measured is the index lookup latency, and we compared the record level index to another index which is already in Hudi. It's called the global simple. That would be the alternative if we didn't have record level index. So when we compare these two indexes, what we see is the index lookup gains a speed up of 17x. The lookup time for the index dropped from 20 minutes to roughly a minute or so. And this also yielded to 2x write performance in terms of the write speed itself. For the other use case, what we did was we took the store sales TP-CDS data set, which is like a 10 terabyte data set. And we ran point lookup queries, that is select and delete on specific records. And there we were able to see like 2x to 3x performance improvement on queries. This is purely on the reading side. And and on this one, we were able to see that with comparing the the table queried with RLI and without RLI. By RLI, I mean the record level index. And that easily gains like 2x to 3x performance. So again, I have linked a table like the blog here that goes through in detail on the design of record level index, what are the caveats, what are the use cases, when to use, and how to enable it, and what are all the future work in the record level index. Feel free to check that out. So with that, now in the last section, we went through how Hudi designs like different indexes to aid these write and read performance. I wanted to see how we can bring all those performance improvements into the Presto Hudi support using the Hudi connector. So that's what I'll be focusing on this section. So remember we talked about the first opportunity for improving the query performance is the metadata, and then we connected that with how the record level index can be used on both write and read side. But that also means we need to be able to read the metadata to understand these indexes from different query engines. That means all the query engines like Presto, Spark, etc. needs to be able to understand the Hudi's metadata table, which is H file format. So what we did was in Hudi 0.15 release, we came up with a technical spec for the H file format. And what that gave us is we can easily implement H file readers and writers across any language, and that can be backwards compatible with any of the existing Hudi storages and the storage format. And we also went ahead building a Java-based H file reader. And this Java-based H file reader has absolutely no dependency on Hadoop or H-based kind of modules. So this is something that we could hook up in the Presto Hudi connector that in future that we can leverage to read these metadata indexes and bring in these query acceleration. Just to note, this is already implemented in Spark and is like fully functional in the Spark pipeline. We wanted to deepen this integration in the Hudi connector just so we have the ability to do that now in Presto. So this is one of the future-facing opportunities where we are looking to spend more time to bring the Hudi connector in Presto to be able to read this advanced indexes. The second one is as we're making the feature capabilities in the 0.x release line, the Hudi community is also pushing towards a bold, strong vision for Hudi 1.x. And in Hudi 1.x, we are reimagining Hudi to be more closer to database-like experience on the data lake. Here you can see like two diagrams comparing what a typical architecture in the a typical database would look like, taken from the seminal paper architecture components of DBMS. And on the right side, how this closely resembles to Hudi's architecture. The green blocks are something that is already available in Hudi, and the Hudi 1.x release line would focus on adding and enhancing existing features or new features. Those are marked by the yellow. And the blue components are something that, along with the query integrations, engines like Spark and Presto can add to these blue components to complete this vision of database kind of experience. If you compare these two diagrams, you would see similar sort of components on both the typical database component architecture and how Hudi 1.x is reimagining this whole lay of land. So this again yields to how we can, for example, if you take a look at these yellow blocks that talks about query rewriting and query optimization layers, that's where we will be able to deepen the integrations on the Hudi connector to be able to make use of more powerful constructs to allow write operations and DDL, DML kind of support using Presto to the Hudi tables. Like I mentioned, we have two new indexes that are already added. Hudi 1.x also envisions adding more advanced indexes into its metadata table. And two have already been added. One is the expression index. It's much similar to how expression index works in Postgres tables. At a high level, it's similar to how you would define an index on a column, but here you define an index on an expression on a column. So if you take, for example, but the power of this expression index is like much more beyond like how a simple index would work. Just to give you some example, right? Like consider a case where you have microservices logging events into like an event log layer. And let's assume these microservices have like an event timestamp TS, and they also have an organization ID, or like represented by org ID. Now, since these are like event logs, you would expect like most of the queries are specific to orgs and are bounded by time range, where you would want to know what happened for a specific org on a time range and debug into those kind of logs. So users naturally tend to partition this data based on org ID and date-based partition, right? So here, assuming that just a back of the envelope calculation, assuming that you have like 1,000 orgs in your company and you want to retain the data for at least 1 year, that would easily end up into like 365 cross 1,000 partitions. And what that means is a large amount of data skew, because we all know that these partitions are not uniformly filled. Most organizations would have like very few data, and few organizations would have most of the data, causing this imbalance, and this would result in a lot of small files. So coming to this point, what users would normally do is like go back, like evolve their partition to just keep it as org ID. And that would result in a physical layout like this, where previously it was org ID and date, and more recently, like after they hit this small file issue, they would move to like a just org ID based partitioning. Here is where this expression index comes into picture. Like expression index doesn't care how this physical layout is. It can easily absorb the partitioning as into the indexing structure itself, and it can still enable data skipping across these mixed type of partitioning. So even if your queries span old and new partitions, expression index would let you achieve the data skipping effects on these different partitioning schemes. So there is absolutely no need for either hiding or evolving the partitions as such. So it's a more profound concept, and it's not something new that Hudi has done, but Hudi has this expression index in beta 1 release if you want to check out. The next index that we build is a secondary index. It's pretty similar to what DB systems would do. If you have queries that have predicates on non-key fields, you would want to build a secondary index, and that's the other index that we built in the Hudi 1.0 beta 2 release. You can check it out. Feel free to try it out and see how that works. But the example here in the sequel is how simple you can create a secondary index in Hudi. With that, I just want to move to the roadmap. Basically, these are areas where we want to, all these indexes are all what we want to extend into query systems like Presto using the Hudi connector. With these deeper integrations, we are able to expand into bringing all these capabilities inside the connector itself and leverage these improvements, much like how we have done with Spark today. Check out the roadmap here. It has like a whole bunch of roadmap for Hudi 1.x, but I thought these two would be like the key epic things to track specific to Hudi Presto, where there are like much smaller activities, or like all activities that are tracked for whatever goes into the Hudi connector. These would be useful to check and track. And of course, if you're interested in contributing to this space, we also have a brand new Hudi Slack channel for specifically for Presto. Feel free to join there. You can also try Hudi 1.x right now. As we speak, the GA release is getting ready for the voting stage. We are actively developing the doc side, and these are all some brand new doc page that has gone through significant updates because of the major release on 1. You could also check out the beta release that is already available in Maven. And This is how you would communicate with us. This is our community. If you like us, give us a star, and subscribe to our socials through LinkedIn and YouTube channels. Thank you. Yeah.
I hope I phrased this question right. So the maximum granularity of pruning via indexes, is that at the file level, or is it at, at like the Parquet file or org file level, or is it more granular? Basically, I was trying to understand, like, is this like something that you push down during during the planning phase so that you just generate less splits, or is it something, is it able to kind of like avoid reading entire portions of the...
Yeah. So it would depend on the type of index as well, but for the record level index at least, the pruning applies to all the equality checks where in or equal to kind of thing, where the equality is based on the record key, so it's easily able to look up the record key to get the locations.
Okay. So then the location then would be the location of the Parquet file?
Of the Parquet file, yes. Yeah.
So we would think of this as kind of like a way to push down filters and such so that we have to
Correct. Yeah.
discover those splits. My second question was, does the H file format have an index? Meaning, like, is it sorted on a particular column? And so, like, would it extend beyond just equality into like range?
So right now, all of the metadata table indexes take H file format, and each of the indexes differ on their purpose and use cases, so it's hard to generalize how the specific index implementation is. But in general, the H file format is what the metadata table leverages. Whereas the top level Hudi table would be something like Parquet or ORC.
Gotcha.
Building on top of that question, did you, in your testing, also test with bloom filters on Parquet files to see, whether that gives you comparable benefit?
Yeah, we already have, I didn't include that in this presentation. So apart from the metadata table indexes that we have discussed in this session, we also have Hudi specific bloom filters on the data files, like not the Parquet ones. And we already use that as part of that's primarily used on the right side. And that's what is in the 0.x primary leverages. With 1.x, we're trying to like consolidate all of this and then move on to the centralized metadata table where the bloom is.
What's the design decision of not using, let's say, a bloom filter already on a Parquet file and building this?
That's more recent, right? Like this was how Hudi started. Like even when Hudi was started, we had the bloom filters in place. More recent is the Parquet bloom filters, like and there are different version mismatches and things like that we need to accommodate for. So early on, we leveraged the Hudi's own bloom filter that is appended to the Parquet file as part of the rights.
But I'm guessing that the Parquet files used by Hudi are for file pruning, but you would still need the Parquet bloom filter for a more efficient row group.
Right, but
Correct.
if you already have the bloom filters on all the Parquet files,
No.
if you submit a filter or like a query, you can still like skip scanning the file because...
Yeah. So
If you were able to retrieve the Parquet bloom filter.
Yeah, just like, I don't know where the bloom filters are stored in Parquet right now, but if they were in the footers, you could just read them out and say, I don't want to read this file at all.
Yeah, you could still use the Parquet-based bloom filter. Hudi has a specific implementation of bloom filter on Parquet that goes beyond the default ones. And it offers like range pruning of the record keys and things like that that does not come by default with the Parquet-based bloom filters. Yeah.
So then I'm guessing like some of this Hudi connector work will involve pushing down expressions that are known during planning.
Correct.
So that we can
Correct. Yeah.
That would be really
Core to that is the DDL and DML support as well. Like so, since Hudi connector is like kind of isolated, we can leverage more of the Hudi APIs to kind of make use of these to build the right support as well. All right. Thank you.